Hey guys, so last time we derived the recurrence relation for our solution, and we discovered that the recurrence relation will be f of n equal f of n minus 1 plus f of n minus 2, where f here represent the number of ways to climb their case of size n. Okay, so that's sorry, that's what f of n mean. And so, for example, if you have staircase with 2 steps, how many ways you can climb it? So if you have 2 steps, so here n is 2. How many different ways? Well, you can go 1 step and then another 1 step, or you can just take one big step. Okay, so in that case, the answer f of 2, it will equal to 2. This will be 2. Maybe I can put it right under it. And then we also discussed in the previous video, you have, for example, f of 3. Well, if you have a staircase of 3 steps, 1, 2, 3, you can go 1, 1, 1. You can go 2 and then 1, or you can do 1 and then 2. Okay. So we said if you have 3 steps, we'll take 3 different ways, which is 1, 1, 1, 2, and then 1, or 1, 2. And here it was 1, 1, or 2. Okay. Okay, and then we ask ourselves, what about f of 4 if it's 4 steps? The staircase was 4 steps. Well, we said if we use the recurrence relationship we discovered, it will be f of 3 plus f of 2, and that will give you 3 plus 2 equal to 5. Okay. And if we use the same recurrence relation, what about f of 5? Will be f of 4 plus f of 3, f of 4 equal to 5, f of 3 equal to 3, you get 8. So basically, I'm just applying what we discovered over here in the last video. Okay. If you're trying to understand where that formula came from, watch the last video, and I drive that formula from scratch. Okay, so what's the problem now? The problem is, I can go different page. If you're trying to calculate, let's imagine f of, I don't know, let's pick some number, f of 10. As we mentioned earlier, that will be f of 9 plus f of 8. Okay, well, we need to calculate f of 9 in that case. Well, f of 9, it will be f of 8 plus f of 7. Okay, and also I need to calculate this f of 8, will be f of 7 plus f of 6. Okay, and so on, and you can see where this is going. Okay, so what's the issue here? There are actually a couple of issues. One of the biggest issues here, we're repeating the same sub-problems over and over. Why is that? If you look at this subtree, this subtree over here, which is calculating f of 8, we're redoing the same subtree over here. Here, for example, you're going to have f of 7 again, and f of 6, and you need to do the summation. Same here. So you notice we have lots of subproblems that overlapping, repeated. For example, if you look at the f of 7 here, we have to do it again here. So there's so much overlapping problems or subproblems, and that's inefficient, okay? So that's the problem with this recurrence relation, okay? If you were to think about it, what would be the runtime? The runtime here. Well, here you're making one function call in this top layer, and then below it, 2 function calls. And then 4 function calls. I'm gonna write as 2 power 2, which is 4. And then you can guess, well, the next one will be 8, 2 power 3. 8 function calls, you're going to have f of 6, you have f of 5, f of 6 again, f of 5, f of 5, and f of 4. It'll be 8. 2, this is... And then I will still need to continue until I reach the very bottom case, which in that case will be all the way until f of 1, which is if you have one single step, staircase with one step, okay? That's a huge tree. It's a big tree, and we're wondering what will be the runtime here. That's the question. Well, let's see. We're adding one function call and then another 2 function calls, 4 function calls, 8 function calls, and it will continue until the very bottom of the tree. So let's think about it. You have 1 plus 2 plus 2 power 2, 2 power 3, and then it will be 2 power 4 until the very bottom of the tree. Okay, well, how many terms are we adding? Well, how many layers do we have here? Well, you were starting from f of 10, the very top, and then you have f of 9 here, with f of 8, and then f of 8, f of 7. So you're going from 10, 9, 8, 7, all the way to 1. Okay? So you're going from 10 all the way to 1, so you have 10 different terms. Okay? So the very last one will be 2 power 9. That will give you 10 terms. 10 layers. Okay? 10 layers or 10 levels in the tree. That's how many terms you're adding. Okay, so you can think of this as 2 power 0, if that helps. 2 power 0, which is the same as 1. All right, okay. And then what? How can we get the summation of this? This is called geometric series. Okay? This is from middle school. If any of you did middle school, you should have studied this. And why is it called geometric series? Because you're multiplying by the same number every time whenever you add. Every damn time you're multiplying by 2, by 2, by 2, by 2, by 2, and so on. Okay, so this is called geometric series. Okay, and there is a formula for it. Okay, the formula is the first term multiplied by 1 minus the multiplication constant minus per n over 1 minus the multiplication constant. This is the first term. This is the multiplication that you're multiplying by every time. So what's the first term? It's 2 power 0. I'm just going to stick 1 instead. 1 minus the multiplication or the factor that I'm multiplying by, which is 2. N is the number of terms. That's the number of terms. We have 10 different terms. From 2 power 0 to 2 power 9, these are 10 different terms. And divided by 1 minus 2, which is negative 1, so you get 2 power 10 minus 1. Okay? Okay, so for staircase, with 10 steps, we need 2 power 10, almost 2 power 10 operations, OPS, operations, okay? Okay, so which means for staircase with n steps, I need 2 power n operations, OPS operations, okay? So what is the runtime in that case? We write this as O 2 power n, where n is the number of steps, okay? 2 power n. That's a terrible performance. Terrible performance. Why is that? Because it grows exponentially. This is exponential rate of growth, obviously, because you're multiplying by 2 every time. And that's pretty slow. Okay. Let's see how slow it is. I'm gonna write some code to show you how slow it is, in case you're not able to imagine that. Okay, let's go to our editor, and over here, and do the base case. Okay, what's the base case? Well, if it's a staircase with 1 step, size 1, then there's only one way to jump to the top of the staircase. If the staircase of size 2 has 2 steps, well then there's 2 different ways. 1, 1, okay, I'm gonna put a comment here, 1, 1, or 2. Here it will be just 2. Okay. Sorry, just 1. Okay, so now if it's anything different from 1 or 2, then I need to use my recurrence relation, and I will need to call recursively, call this method with n minus 1 steps and add that to the same method call, but with n minus 2 steps. That's basically this is basically the comment here. This is literally fn minus 1 that I was talking about earlier plus fn minus 2. This is a recurrence relation that we derived in the last video. So feel free to rewatch it to see where that comes from. Okay? Okay. That's basically it. Let's run it. When n is 2, it's good. N is 3 is good. N is 10 is good. Now let's try to get a little closer to the edge cases. I'll make it to 20. Okay. So I doubled the input size, which is the number of steps in the staircase. Okay, let's see. Okay, so notice here the runtime is O of 2 power n. Okay. Okay, let's make it 30. Okay. So far it's still working. About 35. Still working. Okay, so far so good. Let's push it even a little higher. It's getting slower, isn't it? Getting slower. I wonder why. Oh, because it's O of 2 power n. See? That's a problem. It could even handle 40. That's the issue is O, the runtime of O of 2 power n. Okay? So we need to find another way. This is not good. Okay, so let's recap what's the problem here. The problem is we're redoing the same computations over and over and over. So many times. Lots of overlapping problems. Okay? It would be really, really nice if, for example, f of 7, I only do it once. Wouldn't that be great if I can only just do it once and that's about it? Get f of 7 once and then cache it somewhere and then look it up and then reuse the answer? That would be great. And that will be a topic I'll be talking about next video. But the idea is I do not want to repeat this calculation again and again. F of 7 is done here, also done here, also done here. Look at f of 8. F of 8 is done here, also done here. So we don't want that, okay? So the next video, I will talk about how can we cache these results. We don't have to repeat these subproblems over and over, okay? So I'll see you in the next video.